So, we have not finished, we were discussing about the milk enzymes, right. So, now in this dairy and food process and products technology lecture number 36, we are discussing about the enzymes in milk, right. So, we have already said there are many enzymes present in milk and some more we will tell in detail. Right. So, there are some few enzymes are potentially technologically potential rather few enzymes where we tell that plasmin is one such enzyme. Plasmin is one such enzyme which predominant in indigenous proteins in milk and optimally active at about 7.5 pH and also at around 37 degrees centigrade. It is both in combination that pH and temperature, they do act on the enzyme accordingly, right. So, some enzymes are active at lower pH, some enzymes are active at higher pH depending on that also the temperature and pH, this combination that helps the enzymes to act. So, this is pH as well as the temperature, both are mentioned accordingly, right. So, this plasmin is such an enzyme which is this plasmin and plasminogen, or this plasminogen originate from the mammal's blood and are predominantly associated with the casein micelle in milk used in cheese ripening and stability of casein micelle in UHT milk. So many words we have said, right. Casein micelle we have already said. So, there is no further explanation for that. Then cheese ripening also a little we have said in the previous class that when we are going into cheese manufacturing, then you will see that there are some unripened and ripened cheese, and the meaning of ripening also we have said in the previous class that ripening is one where you develop lot of flavor and odor in the prepared cheese. So, this helps, this plasmin helps to develop such, and these are originated from the mammal's blood, and it comes from the mammal's blood, and it is associated with the casein micelle, right. It also tells about the UHT, another term which we are coming across, that is ultra high temperature, right. We said the other class that pasteurization, right, that is decomposition of the pathogen or destruction of the pathogenic organisms, right. So, and we said it is a time temperature combination. So, always whenever you are heating, it is always a time temperature combination. Ultra high temperature is such a combination where temperature is raised to very high, around say 140 plus degree centigrade, and it is for absolutely fraction of second or second, right. It is called hold, no time. It is hold at that temperature and over. So, that means high temperature, very short time, ultra high temperature. That is also a way of pasteurization, a mean of pasteurization. Another protein called enzyme called lipoprotein lipase, right. Obviously, from the word name lipase we have already said, but lipoprotein lipase, that means it is acting on the lipoprotein, right. Lipoprotein is that lipid and protein together, where there it is, that is called lipoprotein, right, and its optimal activity is around pH 9.2 at 37 degrees centigrade, and relatively heat stable enzyme. Initial digestion and absorption of milk lipids in the intestinal tract and flavor development in certain cheese from raw milk is used, right, and this develops hydrolytic rancidity. The rancid flavor, the other day we said that the rancid flavor in milk is many times associated with fishy flavor, that is the degradation of the your lipoprotein, that is or phospholipid, that is your lecithin, right. So, lecithin where it is there, so if that is degraded, if it is that is decomposed, then it produces trimethylamine or its derivatives, right, which causes the off flavor. So, this lipoprotein lipase acts also on the lipoprotein and it may cause hydrolytic rancidity, right. So, we then get alkaline phosphatase. This we have already said a little. Alkaline phosphatase. Phosphatase is one enzyme which is used to detect whether the heat treatment was sufficient for pasteurization or not, right. That is the phosphatase, because phosphatase we said is the stable enzyme, or compared to other enzymes it is much stabler, and at high temperature when you are pasteurizing, whether it is all organisms have been killed or not, is all pathogenic organisms are killed or not, that is detected by the presence of this enzyme called phosphatase. So, alkaline phosphatase, in short ALP, is such one where the activity is around 9 to 10.5 pH and it works around 37 degrees centigrade. It is relatively heat sensitive and its thermal stability is only slightly higher than that of the non-spore forming. Thermal stability is a little higher than non-spore forming or pathogenic organisms. Normally, pasteurization, which we are referring all the time, is killing of the pathogenic organisms which are not spore former, because spore, if you go into microbiology, you will see that the bacteria which surrounds it like a cocoon, right, like a cocoon is there which protects it. This bacteria is also having some membrane surrounding, some protective cell surrounding it, so that this is becoming very stable, right. Spore formers are very then dangerous. So, we are referring to all the time is the pathogenic organisms which are not spore former. So, this enzyme is little more resistant to heat than the non-spore former pathogenic organisms, right. That is why it is chosen as one of the indicator whether your heat treatment was sufficient or not, right. So, this is the indicator of pasteurization efficiency. Then another enzyme called sulfhydryl oxidase. Sulfhydryl oxidase, right. This is catalyzes oxidation of thiols and formation of disulfide bonds in proteins and peptides. We have already said this is not new, that proteins what, peptides what, that we have already discussed. So, no more. Sulfhydryl oxidase treated UHT milk may have longer flavor retention ability due to reduced lipid or rather lipid oxidation, right. So, if you have sulfhydryl oxidase, it helps in developing flavor in UHT, the reason being the lipids which are degraded by oxidation, that is not there, right. So, that is reduced. So, that is the reason why some good flavor can be retained in the UHT when this sulfide oxidase catalyzes oxidation of thiols for forming disulfide bonds, right. So, that is forming some flavor producing components, not the oxidation of the lipid. Then lactoperoxidase, right. The peroxidase we had said earlier, that is the oxidative enzyme which catalyzes and by the by enzymes are catalyst, right. That we know that enzymes are catalyst. It acts as a catalyst for any reaction, whether good or bad in a material. So, it acts as a catalyst. So, in lactoperoxidase, it is relatively heat stable milk enzyme. It requires 80° centigrade for thermal inactivation. An antibacterial agent which works around pH 8 and exists primarily in milk serum. Milk serum, already we have said where that this distinction between serum, then your plasma, all these things we have said earlier, right. So, it requires 80° centigrade for thermal inactivation and it is a antibacterial agent, right. Lactoperoxidase, that is antibacterial agent, right. So, it is more heat stable, that it is deactivated around 80° centigrade. So, high temperature it can withstand, right. That is why it is in UHT also. Then N-acetyl PD glucosaminidase, right, glucosaminidase, N-acetyl PD glucosaminidase, right, glucosaminidase, that is activity diagnosed for mastitis, that doctors do tell mastitis, right. That is nothing but that infection at the udder, right. Infection at the udder of the animal, that is called mastitis, right, by the doctors. So, this is one term which we have not come across, the mastitis. It is the infection of the udder. So, that infection of the udder can be identified by the presence of this N-acetyl P D glucosaminidase, right. Then catalase, another enzyme which is associated with somatic cell membrane. Somatic cell we have already said. Somatic cell membrane, this is associated with that catalase, right. So, somatic cell membrane can be that catalase we have said earlier is the oxidative enzyme. Xanthine oxidase, it contains all of the molybdenum in milk. Xanthine oxidase, whatever molybdenum present in milk, it is there in xanthine oxidase. So, this is all molybdenum in milk is available in xanthine oxidase. Then superoxide dismutase, superoxide dismutase, not di, sorry, dismutase, superoxide dismutase. This is a protective, this is a protective effect on lipid oxidation. So, on lipid oxidation, this acts as a protection, that superoxide dismutase. Then gamma glutamyl transferase, gamma glutamyl transferase, it transports amino acids into mammary gland. Amino acids are transferred to mammary glands or that glands from where the milk is secreted. That transport of amino acid, that is being done by this enzyme called gamma glutamyl transferase. Then gamma lactose synthase, gamma lactose synthase, it acts for synthesis of the lactose, that is gamma lactose synthase. So, all these are intrinsic in milk, it is there, and we have discussed mostly that these enzymes help differently in different formation or destruction of some good or some bad of the milk, right. So, enzymes do have lot of activities in milk, and there are, as we said, 20 enzymes have been characterized from the milk, and 40 others have been identified as their activity or from their activity in milk. The result indicates that these are the enzymes, those are under that 40 category. So many enzymes are present in milk, which directly or indirectly helping or destroying depending on the enzyme, depending on the use for the milk which we have come across, right. Then we come to vitamins. There are lot many vitamins are there, right from vitamin A, vitamin B2 or vitamin Bs, like vitamin Bs, that is vitamin B1 as thiamine, vitamin B2 or G as riboflavin, nicotinic acid as niacin, vitamin B6 as pyridoxine, pantothenic acid, vitamin C as ascorbic acid, vitamin D, vitamin E as alpha tocopherol, and vitamin K. All these vitamins are present in milk. All these vitamins are present in milk, and we get vitamins out of that, right. All these vitamins are present in milk, that is vitamin A, vitamin B1 as thiamine, vitamin B2 or G as riboflavin, nicotinic acid as niacin, vitamin B6 as pyridoxine, pantothenic acid, vitamin C ascorbic acid, vitamin D, vitamin E, that is as alpha tocopherol, and vitamin K, out of which some are fat soluble and some are water soluble. Fat solubles are vitamin A, D, E and K, and rest of the vitamins are water soluble, right. So, these are all vitamins which are available in milk, but it is poor in vitamin C content, right. It is poor in vitamin C content. You see, it could have been more, but nature, this is a natural product. So, nature has made in such a way. Vitamin C, normally it is this ascorbic acid. So, this is acid component. So, had it been high, then that would have disturbed the pH of the milk, and thereby that the coagulation or the stability of the casein in colloidal form, that would have been disturbed. So, nature has not given that ascorbic acid so much in vitamin in milk, right. So, nature is such a beautiful thing that it controls everything, and with all reasoning, with all scientific reasoning, it is there. And I really appreciate, I am amazed that how nature takes care of everything, right. That is, whether it is good or whether it is bad does not matter, but accordingly nature takes care. So, here that example we have given, that vitamin E or tocopherol, or sorry, vitamin C, not tocopherol, vitamin C or ascorbic acid. Tocopherol is another which is known as the antioxidant, right. We have lot of fats in vitamin. So, antioxidants, as antioxidant, this tocopherol is used, right. And many drugs do have this vitamin E as tocopherol as antioxidant, and that is why milk also do have lot of vitamin E, and it is good to protect the fat as antioxidant, right. Whereas, the other one, vitamin C, is very poor in milk, as well iron. I am not sure about the why iron is so poor in milk, that why nature has made such, but definitely there is some reasoning for that. Yes, iron makes the heme, or it can act with hemoglobin and may come out, I am not sure about that, but definitely some reasoning is also there why iron is so low in milk, whereas so many other things are so high, but iron is so low, right. So, there must be some reasoning, good reasoning for nature to substantiate the reason why it is not present. Okay. Some gases are also there, like milk contains around 7 to 10% by volume of gas, around 7 to 10% by volume of gas. Around that carbon dioxide comes from udder. The udder, when it is being milked, so carbon dioxide do come from there. Nitrogen and oxygen are taken during milking. On standing, the amount of gas becomes less, right. So, when milking is being done, that time lot of incorporation of either air, from there may be carbon dioxide, maybe dissolved nitrogen or oxygen gases are there. So, this dissolved oxygen concentration or amount or quantity is diluted when you are standing for some time, then it comes out, right. As we know that the dissolution of the solution of the gases is a function of temperature also, right. So, the lower the temperature, lower is the solubility, the higher the temperature, more is the solubility. Is it true that with the high temperature, within the oxygen or gases do enter. No, it is the other way, right? It is the other way, right? That is why it is the other way. That is why in drinks, cold drinks typically, when you are putting that cold drink, you see you are putting in refrigerator. Why? Because those carbon dioxide which are put into this cold drink, if at high temperature that has come, though it is sealed, but it at high temperature it has come up, and because of the temperature this solution has happened, it is on the surface of this content or container, and when you are putting back in the refrigerator, this goes back into the solution, and then you get the flavor, you get the you get the pleasure of carbon dioxide being inside, right. So, it is that the lower the temperature, solubility is more, the higher the temperature, non-solubility of the gas is less. This is by and large, exceptions are also there, right. Now, we come to the absolutely concluding part of the milk constituents, that what milk is made of. Vitamins we have already said, gases we have already said, some non-protein nitrogenous substances are also there like urea, amines, creatine, uric acid, adenine, guanine ranging from 1.5 to 10 parts per million, right. So, we come to this level that milk comprised of one side it is water and another side it is total solids. Out of that total solids, it is part is fat which is lipid, and out of that some are true fat, that is several fatty acids or fatty glycerides, and some associated substance. Some associated substances are like phospholipids or lecithin, cholesterol, then carotene, then vitamins like A, D, E and K, right. This is one part, and in total solid another part is total solid not fat, that is solid not fat. So, this solid not fat includes all rest of the other material, and that is this solid not fat is this, that this solid not fat is lactose, that is sugar or nitrogenous substances or mineral matters or some other constituents. In lactose, it is only the milk sugar, then non-nitrogenous substances, out of which it is non-protein substances like urea, amines, creatinine, uric acid, adenine, guanine, etc. In protein, that is nitrogenous substances, it is casein, alpha, beta, gamma, this casein, then lactalbumin or alpha lactalbumin, right. Then lactoglobulin, that is beta lactoglobulin, and protease or peptone, right, protease or peptone. And in mineral matters, we get phosphoric, phosphates, citrates, chlorides of sodium, potassium, calcium, magnesium and traces of iron, copper and iodine. Whereas, in some other constituents we get some pigments, some dissolved gases, some beta B complexes and vitamin C, some enzymes and bacteria. So, it contains everything. It contains everything. So, that is why milk, if it is studied, if dairy, that liquid food is studied, you come across with lot of chemistry and physics and associated things of food. Okay. So, hopefully, we have covered lot in milk constituents, and next we will follow as we have given the outline. Thank you.